Hi everyone! We've talked thoroughly now about finding local maximums, local minimums, and inflection points, so we should be getting pretty good at getting lots of information about functions from their first and second derivatives. What we want to do now is take a step back to something that often is actually a little easier. We want to look at global optimization, so finding global maximums and minimums. This means that we really want to find the biggest y value and the smallest y value for the entire function, not just in some small area of the graph, but for the entire domain of the function. So we're going to start by looking at a definition, and then we'll look at some graphs. Graphically, the idea is pretty straightforward. The challenging part is going to be looking at an equation and trying to figure it out using some calculus and algebra. For the definition right here at the top, we say that if f of p is greater than or equal to f of x for all x in the domain of f, this is where it's different from local max and min. If that's true, we would say that f has a global maximum at x equals p, and if f of p is less than or equal to f of x for all x in the domain of f, then f has a global minimum at x equals p. And just like before, we can categorize the global max and global min together as global extrema. So that would be a general term. Also note that there's alternate language for this, just like we have local max-min and relative max-min are the same thing. Global max-min and absolute max-min are the same thing. So global and absolute, local and relative. Okay, so we get a really helpful thing here. It's the extreme value theorem, and it says that if f is continuous on some closed interval, then we must have a global maximum and a global minimum on that interval. This is pretty fantastic. We're basically getting a guaranteed global maximum and minimum, but there can be some trickiness to this. So let's look at some examples graphically. So in this first one, if we just take the entire graph, we would say, yes, I do have a global max right at what looks like the vertex of a parabola here, but I don't have a global minimum, assuming that these just keep going forever. There is no smallest y value. That doesn't violate the extreme value theorem because we have not chosen a closed interval. So the function has to be continuous on a closed interval to get this guarantee. If I decide to take this function and restrict the domain, let's say this is my A and this is my B, now I'm looking at the closed interval AB, so closed circle at either end, and we're really only considering this middle chunk right here. So I still have the same global maximum, but now I can say that the global minimum happens at x equals b, at the right-hand endpoint. All right, let's look at graph number 2. In this situation, let's say we're restricting the domain. I'm going to put my A here and my B out here. So I am looking, and I'm going to make it closed endpoints again. I'm looking at this and this. So that's all I'm considering. I'm basically completely ignoring anything that happens outside. We can just mentally kind of erase that. So this is my whole graph now. That's my closed interval domain restriction. Here, I think I see a global maximum at x equals b, but I see no global minimum. So I restricted to a closed interval, but I'm still not getting that guaranteed global maximum and minimum. And here again, it's not that the extreme value theorem failed us, it's that we failed the requirements of the extreme value theorem. We do have a closed interval, but the function is not continuous. So f has to be continuous and we have to have a closed interval. If we don't have both of those things, there's no guarantee. We might not have a max, we might not have a min, we might have both, we might have neither. So no guarantees if you don't meet the requirements of the extreme value theorem. Let's look at graph number 3. Here, if we look over all real numbers, the entire domain of the function, I see a global minimum. but I don't see a global maximum. If I restrict the domain, and again, that's fine with the extreme value theorem, it doesn't guarantee anything over all real numbers, only over closed intervals. If I restrict the domain, let's say my A is here and my B is here. So now I'm only looking at this little segment of the graph. I now have a global max at the critical value and a global min at another critical value. So I do get my global max min once I restrict it to a closed interval. Okay, last example, graph number 4. This looks like it may be a sine wave. So let's imagine if it is and talk about what happens over the entire domain. This will sometimes cause a little bit of hesitation. For example, if I say, okay, I think this is the global minimum, people will question a little, well, what about the fact that you hit it again? And remember, that's completely fine. This is the same as local max min. It's greater than or equal to. So as long as there's not a smaller y value, that can be the global minimum. It just happens at more than one x value. So global minimum is whatever, say that's -1 if this actually is a sine wave. The global minimum is at -1, but it happens at multiple x values. And the same would be true for the global max. We hit the global max, we'll hit it again over and over and over again. Let's do this one a little bit differently on the domain restriction. Let's go from A to B, but let's make this an open interval. So these are going to be open circles. That one looks a little crooked, but right idea. So open interval AB this time. I still have the same global maximum, but this time my minimum would be over at this open circle. And when that happens, you would say there is no minimum. And the reason is because in order for you to say that there is a global minimum, you have to be able to say what it is. So let's pretend this open circle is at maybe y equals 0.3. So you can't say that your minimum y value is 0.3 because we don't actually hit 0.3. So maybe you try and say my minimum y value is at 0.31. But that's not actually true because you can hit 0.301 and that's smaller. So then you could try and say, all right, my minimum value is 0.301. But again, it's not actually true because you'll hit 0.3001 and this goes on forever. So you cannot give a smallest y value that the graph actually hits. And that means that there is no minimum. There are other ways to describe the fact that it doesn't go below -0.3, like this graph is bounded by some x and y values. It just doesn't have a global minimum y value. So those are some of the weird things that can happen. Next, I'd like to go back and look at where the global maximums and minimums happened and use that to develop a strategy for finding them. So if I look at graph number 1, the maximum happened at a critical value, the minimum happened at an endpoint. On graph number 2, the maximum happened at an endpoint and there was no minimum. On graph number 3, the max and min were both at critical values. And graph number 4, the max was at a critical value and there was no minimum. So this is a limited set of examples, but I hope maybe we can spot that the key here is that the global maximum should happen at either a critical value or an endpoint. And we're going to develop our methods for finding the global max and min based on that. And we're going to split this into 2. First, we want to look at what happens if we meet the requirements of the extreme value theorem. And then we want to add a little bit more to our strategy for when we don't meet the requirements, because that's slightly trickier. So if the function is continuous and we have a closed interval, the strategy will be to find all of your critical values and then to evaluate at each critical value and endpoint. So this means we're plugging them back into F to find our y values. And here where it says compare values, that's compare y values. So the strategy is actually simpler than local maximum and minimum because we're not asking this subtle question of when does the graph come up and make a peak or when does it drop down and make a valley. This is just saying what is the overall biggest y value and the overall smallest y value. So we don't need to know what's happening nearby our critical values. We just need to know where are all the places that we might find a global maximum or minimum, and that's at closed endpoints or critical values. And then we just plug them all in and list the y values out and say, okay, this is the very biggest y value and this is the very smallest y value. If we don't meet the requirements of the extreme value theorem, we have to be just a little bit more careful. So if we have an open interval or a discontinuity or both, we have to go through that same process as up above. We have to find all the critical values. So that will always be our first step, just like when we were finding local maximums and minimums. We have to evaluate f at each critical value and closed endpoint. So again, same as the previous one. So this is find y values, plug into f, and then we need to do an additional step, but this isn't a step where we would say, oh, actually, this is the global maximum or minimum. It's a step where we might have to say there is no global maximum or minimum. So we need to investigate what's happening to the y values near open endpoints or discontinuities. So what are y values doing? Okay, and again, to be really clear, this second step here, the second part of this step is not to find a global maximum or minimum, it's to say whether or not we even have a global maximum or minimum. So if these are bigger or smaller than y's in first part, then we say there is no global max or min, depending on which way. So if we have a list of y values from the first part of this step, and then we find out that near an open interval, our y values get even bigger, I would say there's no global max. If we have a smallest y value from the first part of this step, and then we find that maybe near a discontinuity, y's are headed to negative infinity, we would say there is no global minimum. So that's what we're actually trying to do here, is to make sure there really is a max or a min. All right, we'll do lots of examples, but hopefully that gets you thinking about how we're approaching this.